So this week we're doing mountain building, deformation, and earthquakes. Here's just some vocabulary that we're going to start with. The word orogeny, that is an episode of large-scale mountain building involving deformation and metamorphism, usually with igneous activity and crustal thickening that results from crustal collisions. So the summary is an orogeny is mountain building. A mountain is at least 300 meters high. It's higher than its surroundings, as opposed to a plateau, which might be land that's 300 meters high, but it doesn't have a restricted summit area. A mountain has a restricted summit area, meaning there's like a peak to it. A mountain range or a mountain belt is a line of mountains. So this map shows you mountain belts around the world. In the last lecture on plate tectonics, we focused on mountain belts that formed as volcanic arcs related to subduction. For example, the Andes Mountains, most of which are volcanic. In this lecture, we will focus on mountain belts that formed from collisions between land masses. The textbook calls these collisional mountains. So some of the mountain belts on this map are collisional mountains, and some of the ones on this map are from volcanic arcs. So a collisional mountain belt results from an event called an orogeny. Orogenies can occur as a result of the following events. Number one, if volcanic island arcs collide with continental crust, or number two, if two pieces of continental crust collide. So these are the two ways that you can get mountains forming. So number one is the volcanic island arcs colliding with continental pieces. That's the top picture. So here's a piece of a continent, and then you have an island arc. And then they might collide, the microcontinent and the island arc. And then number two is two pieces of continents colliding with each other. So going back to number one. Number one was here, volcanic island arcs colliding with continental crust. That results in the formation of a mountain belt. For example, the tectonic orogeny was the result of an island arc colliding with ancestral North America. So this top picture is step one. This is about 543 million years ago. You had a volcanic island arc off the coast of ancestral North America, which is shown here in white, the continental crust. So eventually, this volcanic island arc moved closer to the continental crust, and eventually, the two pieces collided. That happened about 440 million years ago. And that formed the tectonic orogeny, and it resulted in a formation of a tall mountain range. And this, you could see evidence of this actually in New York City. So in parts of Manhattan and in the Bronx. The tectonic mountain belt has since eroded downward to the roots. But in New York City, we see this as Fordham gneiss and Manhattan schist and the Inwood marble. I had previously in older lectures, I showed you pictures from Orchard Beach, metamorphic rocks. That's all part of this tectonic orogeny. And this shows you 3 different stages in the movement of the tectonic island arc as it moved toward and eventually collided with ancestral North America. So the tectonic arc is like this here, right underneath where it says tectonic arc. And then that's 510 million years ago. 470 million years ago, the tectonic island arc has moved northward and is sort of like almost colliding with ancestral North America. And then 450 million years ago, it has completely collided with North America. And then here we have 3 diagrams showing you within the similar, the top one shows you the volcanic island arc from the tectonic. There's North America on the left. Then you have Avalonia, a microcontinent, and then Africa. So here on the left in the second diagram, it shows you the tectonic orogeny. That's where the island arc has collided with North America. Okay, and that formed the mountains that formed in New York City and that now are just eroded downward, and you don't see mountains anymore, but you see the metamorphic rocks. And then off the coast of this mountain range in North America, we had this little piece of continent called Avalonia, and then on the other side was Africa. So eventually Avalonia collided with ancestral North America and formed the Akkadian orogeny. So that formed another mountain range. And that's younger, that was about 350 million years ago. So there was a mountain range and then another mountain range kind of added on top and added next to it. So the second way of forming collisional mountains was continental pieces, 2 pieces of continental cross colliding. So that would be the Akkadian orogeny, where you had Avalonia collide with North America. The current modern day would be the Himalayas. That's the example from modern day. That's India colliding with Asia. Initially, this was a subduction zone. So you see on the top picture, you have India. And then you have a volcanic arc in Asia related to the subduction. And then eventually you had the collision, which formed the Himalayan mountains. Okay, now a lot of this is all related to what we talked about last week in plate tectonics. So then here's a picture of the Himalayan mountains, and you can see they're like very large mountain range. And on the left, it shows you India moving towards the rest of Asia and then eventually colliding. So a local example of a collision between 2 pieces of continental crust is the Alleghenian orogeny, which formed the Appalachian Mountains about 250 million years ago. That is when Africa collided with North America. So if we go back to this, right, A, B, and then C happens. Once Africa actually collides with North America, it's colliding like next to this Akkadian orogeny, which was next to the Taconic orogeny. So, and then that forms the Appalachian Mountains. So if you see like the colors here, the green is the Taconic orogeny. The pinkish purple is the Akkadian. And then now this whole thing is the Alleghenian orogeny. So there were like 3 mountain belts in a row. So these are the ancient Appalachian Mountains, would have been as high as the Himalayas are today. But they've since eroded downward because they're so old and they've gone through erosion. The Himalayan mountains are pretty young. If you see here, this collision is only like 10 million years. So mountains that form as a result of a collision or an orogeny, as opposed to island arcs or the volcanic arc mountains, like the Andes Mountains. So the collisional mountains contain a lot of sediment and sedimentary rocks that have been folded and faulted. They contain evidence of regional metamorphism and evidence of igneous activity. So you're gonna have a lot of large bodies of magma underground. And you can see that like here, where you have all this magmatic activity. Then we have the word terrain. Island arcs, for example, Japan or the Philippines, and small crustal pieces like microcontinents can become accreted onto continents. So those are called terrains. So in Western US, the terrains are from all different areas. They have different origins. Some of the pieces are pieces of ocean crust, some are pieces of just other continental pieces. Whereas in the eastern coast of the United States, we have remnants of this microcontinent called Avalonia. And we have remnants of this tectonic volcanic arc that got added onto North America. And then we have pieces of Africa that collided with North America as well. So all of those together make different terrains that get added onto North America, or any land, basically. So here are the terrains in New England. The shaded in area is Avalonia. Okay, so that was that extra microcontinent that collided with North America. And part of it stayed there. So that's your Avalonia. Okay, the microcontinent. And then we also have the pieces from the tectonic arc that collided with North America as well. So what is the anatomy of a mountain belt? Here's a cross section of a mountain. Mountains contain thick roots that project far below ground, like ice cubes and icebergs, where only part of the ice is above the water. So you see here, the continental crust is protruding downward into the mantle. And then it also goes upward as the mountain. Okay, so that's like the root. Also like your tooth, okay? Your teeth have a root that goes like way into your gums and in your jawline. That's like the mountain, right? You only see the tooth popping up. So you only see like the mountain popping up. You don't see the root. So what about erosion of mountains? Remember, the Earth's crust floats on top of the denser mantle because of buoyancy. Erosion removes upper layers of rock from mountains. As rock is removed, the mountains do not push into the mantle as much as they did before the erosion. So what happens is crustal uplift. The crust rebounds and becomes uplifted as erosion removes material from the mountains. The uplift is related to the process of isostatic adjustment or isostatic rebounds. Ultimately, the land that used to be mountainous reaches equilibrium and becomes relatively flat once again. So isostatic rebound is the unloading of the crust that causes it to rise until it reaches equilibrium. So that's similar to if you have an empty boat in the water, the boat is like lying higher up in the water because it's empty. If you put a whole lot of items into the boat, it causes the boat to sink lower into the water. If you were to remove those items from the boat's gonna rise higher in the water again. So if you erode the top of the mountain is not gonna push down into the mantle as much, it's gonna rise back up. That's rebound. So we can look at this diagram as well. If you look at the top picture, it shows you a young mountain range. And then eventually you have erosion off of the top of the mountain and then deposition of sediment on the outskirts of the mountain. And then the mountain is not pushing into the mantle as much because the mountain has less material. So you see the root of the mountain is rising. So that's the isostatic uplift. And then eventually at the bottom diagram, you end up with more like flat land because as the isostatic uplift happens, you have more erosion happen. So eventually the land ends up flat again. And that's when there's equilibrium. Here's another diagram of the same thing. So you have a young mountain range. And then you have erosion from the middle of the mountain, deposition of the eroded material on the outskirts of that mountain range. So you're like making the mountains flatter, but you're adding material to the outside of the mountain. Eventually, you're left with flat land. And you can see in these photos that is what happens as well. Okay, and then we also talked about this in the metamorphic chapter where it was exhumation, where you had the mountain range, and then over time, the metamorphic rocks that form deep within the mountain are brought to the surface. Okay, so let's take like a 10-minute break. Okay, 10-minute break, and then we'll come back and start on the next section. Okay, so 10-minute break. I'm gonna stop the recording. So this section of the lecture is on deformation. So before we talk about deformed rocks, we're going to talk about what undeformed rocks means. So undeformed rock layers are generally going to be flat, horizontal layers. And that is because of the principle of original horizontality. That tells us that sediments are deposited in horizontal layers. Therefore, sedimentary rocks will also form as flat horizontal layers. So this top diagram here shows you just flat layers of rocks. And we talked about this when we did sedimentary rocks as well. If sedimentary rocks are found to be in any other orientation, for example, tilted on an angle or folded, then that tells us that the rocks were deformed in some way. Like the bottom picture, they got folded. And that's through like tectonics and mountain building events can cause folding and tilting. So at several kilometers below the Earth's surface, rock layers can fold under high pressures and temperatures. We're talking about high pressure and temperature that's not hot and pressure enough to cause metamorphism necessarily. Like you could have folding, but not actually have metamorphism. It depends on like the range of temperature and pressure. So at shallower depths, closer to the surface, where rocks are exposed to cooler temperatures and lower pressure, rocks are gonna fracture. So there's a difference between fracturing and folding. Some other vocabulary here. Stress is gonna be forces that are applied to rocks. Strain is the reaction a rock has to stress. And deformation is related to strain. It's any change in shape or volume of rocks in response to stress. When stress is greater than the internal strength of rock, the rock will become deformed. This diagram shows you different types of stress. The top row is shallow. The bottom row is deep, depth under the surface. Okay, so how rocks respond to differential stress. Compression is when you have a collision of some sort where the arrows are moving towards each other. At a shallow depth, that's going to cause something called reverse faulting or folding at deep depth. Tension is like a pulling apart force, and that causes either what's called normal faulting or stretching. Shear is when you have like a transform fault where you have like going opposite directions of movement but next to each other. That causes faulting, like a strike slip fault, or something called shearing or bending. So there are different types of strain or how rocks react to stress. Elastic strain is when deformed rocks return to their original shape when the stress is removed. So that is not a permanent change. Plastic strain is when rocks react to stress by folding, and that is a permanent deformation because the rocks will stay in the folded shape. Now, elastic material behaves with elastic strain, and plastic material behaves with plastic strain. You know, if you look around your house for like plastic and elastic stuff, they behave in the way that, you know, plastic and elastic behave. Fractures are when you actually have the rocks break, and that's permanent deformation as well. Okay, so we're basically just on slide 27. So here's an example of elastic strain. If you apply stress to a tree branch, or a Twizzler, or a rubber band, or a piece of elastic, and then release the stress, the material will return to its original shape. There is no permanent deformation. So I have this picture of a pine tree when it snowed, and the weight of the snow bent the branches. But then when the snow melted, it released that stress and the branches went back to their original shape. There was no permanent deformation. An example of plastic strain is stress applied to something that's movable, like Play-Doh or plastic or aluminum foil. So here was this random piece of plastic, and I bent it. I permanently bent that piece of plastic. It's now in a deformed new shape, and that's a permanent change until you go ahead and push it into a different shape. Okay, it's not like it bent back into its original shape like a piece of elastic would. So the type of strain that occurs depends on a few different factors. The kind of stress applied, if it's tension, compression, or shear stress. That's this, compression, tension, shear. How long the stress is applied for and how much stress is applied. The rock type affected. So like soft sedimentary rock versus hard metamorphic rock. Pressure and temperature conditions under which the stress is applied. So that means like the depth beneath the Earth's surface. Rocks are more ductile or easily molded and shaped at depth and more brittle closer to the surface. Ductile rocks exhibit plastic strain before fracturing. Brittle rocks exhibit no plastic strain before fracturing. And this is a diagram that shows you brittle rocks are closer to the surface and they're more likely to fracture. Ductile rocks are at a particular depth and they are more likely to fold. So if we go back here, the shallow rocks are going to fracture and the deeper rocks are not. They're folding and stretching and shearing, but they're not fracturing. So now we're going to talk about fractures in rock. So fractures in ductile rock, plastic strain is a ductile rock is going to exhibit plastic strain before it fractures. So here I had this paper clip and I bent the paper clip so it was undergoing plastic strain. But if you bend it enough in a certain way, it will actually just break and crack. The same concept can also be shown with an old credit card. You can bend the credit card until it cracks, but you're bending it, that's gonna be plastic strain. And then once it cracks is the fracturing. Then you have fractures in brittle rock, though that's when the rock is closer to the surface and it is gonna be brittle. Those types of rocks are going to fracture without exhibiting plastic strain first. So that's like a piece of chalk or like a Kit Kat bar or like a hard pretzel, where when you go to crack it, it cracks right away. There's no bending first. So like pretzels and Kit Kat bars break like a brittle rock, whereas like a credit card will bend first and then crack. So that's the difference between what happens in a brittle rock closer to the surface versus a ductile rock deeper down. Which one breaks easily? Yeah, brittle is gonna break easily. Yes. So then what are the geologic structures caused by deformation? Folds, joints, and faults. Folds form when rock layers that used to be horizontal have been bent. Folds are a result of compression stress. Again, you have to look back here. Compression is when the arrows are moving towards each other. The top left here, it says compression. So that's the arrows moving towards each other. You're gonna get folding. Okay? And this is a monocline, which is just one simple bend in the rock layers. Folding usually takes place deep in the crust where the rocks are more ductile. Here's more pictures of folds. More pictures of folds. More pictures of folds. Now, when the fold arcs upward, like the left-hand picture here, that's called an anticline. And when it sinks downward, it's a syncline. So I don't think there's a way of me drawing on here. Let me see if I could do it. Okay, so when you look at an anticline, it kind of looks like the letter A. Okay, so A for anticline. When you look at a syncline, it almost kind of looks like a basin, like a basin, like a sink basin, right? So a syncline looks like a sink. Okay, so A for an anticline looks like the letter A. Syncline looks like a sink. Okay, and then this shows you anticlines and synclines. Lots of folded rocks. Okay, and then we have these two diagrams here where I'm asking you which diagram shows an anticline and which one shows a syncline. They are actually labeled A and B on the bottom. So the diagram on the left is what? An anticline or syncline? Well, no, I'm saying is the diagram on the left an anticline or a syncline? Correct, it's an anticline. The diagram on the right is an anticline or a syncline? And I even have like the letter A and then a picture of a sink. Just kind of like as extra hints. Right, so anticline on the left, syncline on the right. Another type of deformation is joints. joints are fractures in rocks where no movement has occurred along the fracture. For example, columnar jointing in basalt rocks. We did that when we did igneous rocks. Or joints like this, where you look on the, you look in this photo and there's like all these joints that are in the kind of a pattern, like a cube pattern, right? It looks like squares. Then we have faults. A fault is a fracture in which blocks of rock on either side of the fracture have moved parallel to the fracture surface. What that means is this. Let me show you. Okay, so this is the snipping tool, which I think is one of the best programs on a PC. It's like my favorite program. Okay, so anyway, you look at this rock layer here, and then look at this rock layer here, and you kind of see they look like they match, right? But they're not connected any longer. Like they used to be connected in one line, but now they're separated. This is the fault line. So when you look at the pink lines, this side of the rock, this side of the fault looks like it moved up, and this side of the fault looked like it moved down. So that is a fault because there's movement on either side of that fault line. Does that make sense? Okay, so there were different types of faults. We're gonna start with dip-slip faults. That's when all the movement on the fault is vertical. So you either have up or down along the fault plane. What's this? Hold on. For question 2 on the review sheet, how would we draw a reverse fault? We are going to get up to that in a minute. Okay, so a normal fault is when something called the footwall block moves up relative to the hanging wall. This will make more sense after we actually do them, but when you go back and study, you'll see this page. So you're gonna remember FUN for fun. A reverse fault is when the footwall block moves down relative to the hanging wall block. You'll remember FDR. A thrust fault is when the reverse fault on which the fault plane dips less than 45-degree angle. What? Wait. A reverse fault on which the fault plane dips less than a 45-degree angle. Yeah. Okay, let me move on. So this is a fault, and you have a person standing in the middle there. And I'll show you why. This guy right here. There's like a geologist in the middle of this section where it says footwall and hanging wall. So footwall is what you call the side of the fault where the person's foot is. But you're just like pretending that there's a person in here. There's not really a person inside the fault. You're just using the person as a way of determining if it's a footwall or a head wall. So the footwall is if your imaginary person's foot would be on that wall. The hanging wall is where the head is. Sometimes it's also called the head wall. So in this case, you're going to look for rock layers. And when you find some rock layers that look like they match, you're going to see if they went up or down. Let me show you what I'm talking about. Okay, so in this case, you have like this rock layer here, looks the same as this rock layer here. If this is your foot wall on the left, because that's where the guy's foot was on this side, if you forget, just like draw a little person in there. The blue thing in the middle that looks like a lollipop with hands, that's a person. So the feet are going to be standing on the foot wall, and then the head is on the head wall or the hanging wall. So in this case, the foot wall looks like it went up relative to the hanging wall. So if the foot wall moves up, we call it a normal fault. F-U-N. Okay, so foot wall moves up, it's a normal fault. Does that make sense? So a normal fault is a fault that had the foot wall move up relative to the hanging wall. That's just what it is. Now, also people like sometimes think that it looks like, wait, I'll get to that in a second. I'm gonna move on. Okay, so here is my little depiction of how to determine the foot wall and the head wall. So I took a fault line and I separated the fault line so that you could see the foot wall is where you're standing on top of, and then the head wall or the hanging wall is where like you'd bump your head if you were at the fault line. Some people think this is more confusing than this. So if this confuses you, then don't use this. Okay, so then here is a normal fault. Again, the foot wall block is moving up relative to the hanging wall. If the foot wall moves down relative to the head wall, then it's a reverse fault. And we could say FDR, like the president. Also, reverse faults tend to look like the letter Z. Now the Z could also be backwards, but it's the letter Z because it's like, it's an acute angle. It's like a small angle, less than 90 degrees. So it looks like the letter Z. So which of these diagrams represents a normal fault? So what I would do is draw a little person in the middle. Draw like a really tiny person. Oops. Okay. And if you were to imagine that person walking up one of these surfaces, it's like, which surface can you walk up? Am I sharing the right thing? No. Oh, yeah. So in diagram 2, the foot wall moved up. So this is foot wall, head wall, foot wall, head wall. It's an F. Okay, yeah, so diagram 2, the footwall has moved up relative to the head wall. So that's a normal fault because FUN. And then diagram 1, the footwall moved down relative to the head wall. So that's a reverse fault. Now also we can do like the whole letter Z thing, right? That's a really bad drawing of the letter Z, but I'm trying. Okay, so you have it's Z, but it's backwards. But in this case, it's like a more open angle. You guys see that? So in normal fault, it's a more open, obtuse angle. It doesn't look like the letter Z. A reverse fault has like the letter Z in it. Hopefully this makes some sense. Okay, so then we have another type of fault that's all horizontal movement. The dip slip was all vertical, so it's up or down. Strike slip faults are all horizontal movement, just next to each other. And that's due to what we call shear stress. And you kind of have to go back like all the way here. Shear is like on this diagram here. Okay. The San Andreas fault is a transform plate boundary that has a strike slip fault. Okay, so the San Andreas is a strike slip fault, as we see here. This is an overhead view of the San Andreas fault. Now, by the way, Los Angeles is on the Pacific plate, whereas like most of the rest of the United States is on the North American plate. So LA is on a different tectonic plate. I don't know if you find that interesting or not, but I think it's pretty cool. San Francisco is basically on the San Andreas fault. So what would you expect to have happen, like a geologic event would happen in San Francisco? Yeah, they have earthquakes there because they're on the fault line, San Francisco. Yeah, they got lots of earthquakes there. Okay, so here's another picture of the San Andreas. This is what it looks like. You can actually see the fault like in the land. I don't know exactly where this is on the San Andreas fault. It doesn't say, but this is along the San Andreas. And then this is a summary of the different types of faults. So your normal fault is when you have tension stress or pulling apart stress, where the arrows are moving away from each other. Reverse fault is compressional stress related, when the arrows are moving towards each other. A strike slip fault or transform fault is horizontal movement. And the thrust fault is a low angled reverse fault where the dipping is less than 45 degrees. Okay, so going to so going to the review sheet, excuse my messiness, but the question was, how do you draw for question 2, how do you sketch these things? So like the normal fault, I drew like that. And then for the reverse fault, I drew like that. And the transform, I drew like that. Okay, so however you want to draw it, you can actually draw it like 3D if you want, like the diagrams, or you can draw it like this. You're welcome. Okay. Oh, so like for the transform fault, it's basically an overhead view. That's what that says, overhead view. And then the other two are like a side view. Okay, so then types of faults and the plate boundaries they are related to. Which type of plate boundary is this type of fault related to? So your plate boundaries include convergent, divergent, and transform. Correct, this is going to be your transform boundary. Okay, and then your normal fault is going to be related to what type of boundary. Now, if you look at the arrows, wait, was someone just saying? I didn't hear. If you look at the arrows, it will probably remind you of one of the plate boundaries. Arrows moving away from each other. What type of boundary is that? Correct. Divergent is when the arrows move away from each other. So the normal fault is related to a divergent boundary. And then here is a reverse fault related to compression. And if you look at the arrows, they're moving towards each other. So what type of plate boundary do you have arrows moving towards each other? Correct, convergent. The first one is the, what do you think the first one is? The choices are transform, convergent, or divergent. Yes, transform. Okay, so then let me just open up the review sheet. So in the review, we have this little chart here. So let's take a few minutes, try to fill this in, and then we can go over it. Now, if you did not print this, where it says sketch, you could just sketch it on a piece of paper. Okay, so take about 5 minutes. I don't know if you may need more time than that, but okay, so for example, compression stress. You're gonna draw the arrows that indicate the movement related to compression stress. And when you go to the lecture, we talked about this, it's on slide 26. Okay, so slide 26 is this. So you're using this and your knowledge of what we just learned about with the faults and everything, and your knowledge of plate boundaries that we did last week to fill in this chart. Does that make sense? Okay. So let's take until like 2:30. So that'll give you like 7 minutes. If you don't know what you're doing, if you don't know what you're supposed to be doing, then let me know. You're filling in the chart on the review sheet. I mean, I could pause the recording. So next I have this folding and faulting with mountain building, and then there's this video. So I am going to show the first 3 minutes of the video. Okay, so the next part of the lecture is earthquakes. Have you ever experienced an earthquake? Where were you and what was it like? So has anybody ever experienced an earthquake? Nope. Well, if you have, then say yes. We'll do it that way. No? Okay. So do you want to explain to the class what it was like? You can unmute yourself and speak, or you could write it in the chat. It was very subtle. Okay. Okay, anyone else ever in an earthquake? No? Your desk shook? Oh, wow. Okay. Yeah, it depends on where people are. Like, if you are in another country where you have a lot of earthquakes that are pretty strong, you would have a different type of story than if you are in New York or New Jersey and you have a really small earthquake that you like barely felt. Yes, on Long Island, there was an earthquake. Depends on the magnitude. Yes, the magnitude of the earthquake, the one that we had in Long Island, it was right after Hurricane Irene. So Hurricane Sandy was 2012. Hurricane Irene was 2011. So the earthquake that you're talking about was probably 2011, because that's the one that I felt. Yeah, I think it was in Virginia somewhere was the epicenter. Yes, so I felt that one too, and I felt like I thought that like the house I was in, I thought was falling down or something because something that was on the roof fell off the roof. I don't know if there was like a brick on the roof or something, but it like rolled down the side of the roof and like off the house. And so when I heard that, I thought the house was falling. I didn't know what was happening. I did not think immediately, oh, it's an earthquake. I didn't know what was happening at first. But then once you start feeling like a swaying motion, then that tells you it's an earthquake usually. So I felt like a bump feeling, like a vibration, like just a bump. But then I felt the house swaying back and forth, kind of like the floor was swaying, kind of like in a rhythm. And that's when I realized we were having an earthquake. But nobody else felt it because I was upstairs and everyone else was downstairs. As you go up to higher levels in a building, you're more likely to feel the earthquake. If you're on the ground level, sometimes you don't feel it. So no one else knew what I was talking about. And I was like upstairs yelling that we were having an earthquake and no one else felt it. So that was a little weird too, because I was like, no, we're having an earthquake. I'm telling you, this is what happened. And they're like, no, what are you talking about? So that was kind of strange. It was a very strange experience. But yeah, it was a very small earthquake. It was, it was something you felt, but it wasn't like really, really, really bad. So using your knowledge of plate boundaries, what part of the US do you think an earthquake is likely to occur? Okay, and I've had students who told me like they were in another country and they experienced really strong earthquakes. That definitely happens as well. Like if someone lives in Dominican Republic or Puerto Rico or Turkey or Japan, or like Pakistan, there's going to be earthquakes. Okay, so where in the United States do you think an earthquake is likely to occur? So I'm trying to like zoom in a little bit more. Right, California. And why is that? Right, next to the San Andreas Fault. Now also you have another fault further up north along like Washington and Oregon State, where you have a subduction zone. It's a little tiny subduction zone where this Juan de Fuca plate is subducting beneath the North American plate, just in this little area. And it forms the Cascade Mountains. So you have earthquakes there too. Many of you did a plate tectonics lab in your lab class. Not everybody did it, but there is, so if you did the plate tectonics lab, you discussed similar things, like where earthquakes were related to plate boundaries. Okay, so earthquakes are most common along plate boundaries. Most common, 80% of earthquakes occur in the circum-Pacific belt. That is along the Pacific plate boundary. Okay, so when we look at the Pacific plate here, Around the Pacific plate is where most of our earthquakes occur on Earth, and that's the circum-Pacific belt. Circum just means like around, like a circumference. So it's around the Pacific is the circum-Pacific. 15% of earthquakes occur in the Mediterranean Asian belt. Less common is 5% of earthquakes occur in plate interiors and mid-ocean ridges. And this shows you earthquake locations between 1963 and 1998. So the black dots are all earthquakes. And this is over 350,000 earthquakes. So when you map out all these earthquakes, the locations match the plate boundaries map. Okay, the maps pretty much map. The maps match, yes. Okay, here's another diagram showing the same thing. This shows you where your transform, divergent, and convergent boundaries are. And then the yellow dots are your earthquakes. And then it shows you also where the ring of fire is. Okay, so this is your earthquakes along with your plate boundaries on the same map. So what is the main reason the east coast of the US is a low risk earthquake zone? Yep, it's in the middle of a plate. Okay, we live in the middle of the North American plate, so we are very far from plate boundaries. Okay, if you look, right, you look on the map, we are far from plate boundaries. We do occasionally experience earthquakes on the eastern coast of the US, even though we're not an active plate boundary. Why might we experience earthquakes here, even though we're not next to an active plate boundary? Anyone think they know? Why might we have earthquakes here sometimes? Even if we're not near an active plate boundary. Think about it for a minute. Let me know what you think the answer is. You're close, but that's not exactly, you're close though. Very close to the answer, but not exactly. So what you were saying before was that the earthquake we felt on Long Island in 2011, the epicenter or the actual earthquake happened, let's say, in Virginia. What's going on is we have ancient mountain ranges that run down the East Coast. Very old mountain ranges related to when there used to be plate boundaries. So if we go all the way back to the beginning of the lecture, and we look at something like this, the Appalachian Mountains, when North America collided with Africa. Or when we see the remnants of the tectonic orogeny, that was a convergent boundary. We have all these ancient mountain ranges, ancient converging that happened. So the ancient convergent boundaries leave fault lines. So we get fault lines related to the time when we used to be at an active plate boundary, right? So this is North America colliding with Africa, forming the Appalachian Mountains. So the Appalachian Mountains, even though they formed like, 250 to 300 million years ago, there are fault lines within the Appalachian Mountains from when they formed, okay? Because that used to be an active plate boundary. Okay, so the reason why we get earthquakes on the East Coast is because there were ancient fault lines. So it's ancient fault lines from when we used to have an active plate boundary. Okay, so now what is an earthquake? There's faulting, which we talked about. So the earthquake is the shaking or the trembling of the ground due to a sudden release of energy related to the faulting. So it's like the vibrations that go through the earth from the cracking of the rocks associated with the fault. The aftershocks are just continuation of the fault. So you may have a fault and the movement along the fault may still need a little bit of adjustment. So it's like more faulting happening along the same fault. It's more movement. Now the aftershock can be smaller than the initial quake, or actually, aftershocks can actually be pretty big. Okay, aftershocks can still be dangerous and shake the earth quite a bit. So what causes an earthquake? The elastic rebound theory is that rocks can bend when they undergo deformation, and that builds up what we call potential energy. So if you were to bend a plastic ruler, the ruler stores the energy that will be released if it cracks. So let me kind of show you how this works. So I have this ruler. I don't want to break it though. But if I bend the ruler, if I bend it to just like that amount, if I continued bending it, it has potential energy now. So if I let go of like my right hand, the ruler would fly across the room. Okay, it's like stored energy because I'm putting pressure on it. If I continued to put this pressure on the ruler will keep bending until it cracks. Once it cracks, it's no longer in the bent shape. It goes back to being flat. It's going to be broken in half, but it won't be bent anymore. It goes back to being flat. So that's what the elastic rebound theory is. Okay, so it's like bending the ruler, holding in that potential energy, And then once you snap the ruler, that's like the earthquake happening. And then the rocks all will go back into their original shape after the rupture. Okay, so here straight is a shape, bent is a different shape. Once it cracks, the vibrations happen from the cracking, that's the earthquake. And then the ruler goes back to being straight, although it happens to be in half. But being in half does not change the shape of being straight. That's why it's elastic. It's going back to the original shape, which is a straight line. So when the strength of the rocks is exceeded, that would be like if I broke the ruler after bending it too much. The release of energy happens when you crack the ruler because you bent it too much. The release of energy underground in the rocks is when the rocks crack and have that fracture. Okay, and then the rocks will go back into their original shape, although broken. Okay, so here we have the deformation of the rocks next to the deformation of a stick. Okay, so you're starting out with a pre-existing fault line, and then the deformation of the stick did not happen yet. Okay, and then you have movement on opposite sides of that fault line that's similar to starting to bend the stick. And that's when you're storing the potential energy. And then once you exceed the strength of the rocks or exceed the strength of the stick is going to crack and the rocks are going to crack. And that's when your earthquake happens. And then after the crack happens, the rocks return to their original shape, although they're in a new location. And your stick cracks in half, but it goes back to being straight, which is a shape. So that's the elastic rebound theory. So where does an earthquake begin? It begins at the focus. The focus is the point underground where the energy of the earthquake is first released. So that's underground where the fault line happens, where the fault line forms. And then seismic waves or earthquake waves radiate from that focus. Directly above the focus on the Earth's surface is called the epicenter. Okay, and this shows you the focus underground and the epicenter is directly above the focus. The focus is on a fault line, and then you can see the seismic waves radiating outward from the focus. There are three categories of earthquakes based on their focal depth, which is the depth of the earthquake focus. So you have shallow focus earthquakes with the depth below the surface is maximum 70 kilometers deep. An intermediate focus earthquake is 70 to 300 kilometers deep. And a deep focus earthquake has the focus that's 300 kilometers to 660 kilometers. 90% of foci of earthquakes occur less than 100 kilometers below the surface. So most earthquakes are shallow to slightly intermediate. And this shows you the plate boundaries compared to focal depth. So divergent and transform boundaries are always shallow focus earthquakes. Convergent boundaries can be shallow, intermediate, and deep focus. If they are deep focus earthquakes, then it occurs along the subducted ocean crust plate. And this shows you focal depth along with plate boundary. So on the bottom, it shows you depth, and then it says it's like yellow is 0 to 70, orange is 70 to 300, and then 300 to 800 is red. So this shows you where the different plate boundaries are, and it shows you if it's a shallow focus, intermediate, or deep earthquake. So most of the deep earthquakes are occurring around what plate? What tectonic plate has most of the deep earthquakes around? Anybody? Most of the deep earthquakes are surrounding what plate? No, like which plate? What's the name of the plate? Okay, that's the Pacific plate. The area where the red, where most of this red is in the center of this map, that's the Pacific plate. Right, it's convergent plate boundaries. That is correct, but this is the Pacific plate in the middle there. So why are convergent plate boundaries associated with deeper earthquake foci? It's related to subduction, which brings hard, rigid rock deep into the mantle. Otherwise, the mantle is too soft for earthquakes to occur. So when you're bringing down the ocean crust in the subduction zone, that's allowing earthquakes to happen deeper down in the mantle, whereas normally you cannot have earthquakes that deep. Okay, you could read through this on your own. Okay, so how are earthquakes studied? Seismology is the study of earthquakes. Seismographs, that's the equipment that detects, records, and measures seismic waves produced by earthquakes. Seismogram is the written record that comes from a seismograph. And this picture here is a seismograph. And this is another seismograph. So it has like this drum that rotates, and there's a pen. And the pen is picking up earthquake waves. And then it vibrates. And the amount that it vibrates will produce the earthquake waves on a piece of paper. So you get like this earthquake graph. That's your seismogram. This is what a seismogram looks like. The first wave from an earthquake that's going to reach the seismograph is what we call the P wave. The second wave that reaches the seismograph is called an S wave. And then we get what's called surface waves. So you read this from left to right. And it says on the bottom, earlier, later. Okay, so the first wave to reach is a P wave, and that's going to be drawn on the piece of paper, a little blip. Then you have some time in between, and then you have another blip, that's your first S wave. And then you have surface waves, which are like a lot bigger in amplitude on the graph. So this shows you a focus where they're seeing it's the hypocenter. That's the focus of an earthquake. And it's showing you 3 different locations of seismographs. So seismograph 1, seismograph 2, and seismograph 3. And the earthquake information changes depending on how far away you are from the focus. So you can see, like, as you get further away from where the earthquake happened, the surface waves are smaller, for example. And then if you get really far away, the S waves and the surface waves take a longer time to reach the seismograph. Okay, seismic waves. That's the energy released from an earthquake that radiates outward. Those are seismic waves. There are 2 categories of seismic waves. Those that radiate outward and throughout the solid earth, like sound waves, those are called body waves. And then you have waves that travel through the surface of the earth only. They don't go through the whole earth, they just go through the surface material. Those are called surface waves. So here's a summary of the 2 different types. Body waves radiate outward from the focus and throughout the solid earth like sound waves. Those include P waves, which are primary waves, and S waves, which are secondary waves. Surface waves travel at the surface of the earth, and those are going to include what we call Love waves and Raleigh waves. So these are your body waves. Your P waves are the fastest seismic waves, and they're the first to arrive at a seismograph. They can travel through solids, liquids, and gases. And they act kind of like a slinky, like a spring, okay, where the wave motion kind of moves like the picture is showing you. S waves are slower than P waves. They travel only through solids, so they can't go through the liquid outer core. And their movement goes like up and down, like this string that's like going up and down in the diagram here. Okay, so this shows you the P wave direction and movement. So these are like compression waves where like parts of the wave will compress and then other parts are expanding. And then this is how an S wave travels. S waves, again, they can't travel through liquids, only solids. P waves can travel through both liquid and solid. So this red X is an epicenter of an earthquake. The outside circle is the crust of the earth, and then we have the mantle labeled in yellow, and then the liquid outer core. So the S waves are traveling from the epicenter, and they stop at the outer core, but the P wave is able to keep going. So S waves cannot go through the liquid outer core. And we have surface waves travel at or just below the surface, and they are more damaging than body waves. They are slower than body waves, so they arrive at the seismographs after the body waves. And those include Love waves and Rayleigh waves. So Rayleigh waves act kind of like waves, like these circle orbital movement. So you will end up getting like waviness in the land from the surface waves. They'll cause like these waves in the earth. And then your love waves are like a back and forth motion. If you look at the red arrow on the side here, it's like a back and forth motion, side to side. So this is showing you damage to surface waves from the 2015 earthquake that happened in Nepal. Surface waves are more damaging because they have a higher amplitude. Amplitude is how high the graph goes. So when you look at the P waves, the S waves, and the surface waves have a higher amplitude. They go up and down more on the graph. So there's more shaking involved. And like all the movement is centered around the surface. So surface waves are going to be more destructive to the buildings that are there. Structures built on weaker material like loose sediment or mud can experience more shaking and thus more damage than similar structures built on bedrock. So that's the relationship between seismic wave amplitude and underlying geology. You have a higher amplitude and more shaking when you have buildings built on weaker material. So what else can happen related to earthquakes? Liquefaction, tsunamis, ground failure or landslides, and fires. The fires are due to like broken electric lines and gas lines, not because an earthquake is just causing a fire. So liquefaction is from ground shaking of water saturated soil. So these are earthquake resistant buildings in an area of Japan. During a 1964 earthquake, these earthquake resistant buildings fell over. That is because of liquefaction. So when you take soil that has some moisture in it and you shake the soil and vibrate it, over time, you get like a liquefying effect where the soil temporarily is not acting like a solid, it acts more like a liquid. So then the buildings just fell over because of that. So, okay. Tsunamis are caused by submarine earthquakes, but also submarine volcanoes and submarine landslides. Tsunamis can travel across entire oceans at a speed of like 600 miles per hour. For example, the Indian Ocean, there was a 9.0 magnitude earthquake under the ocean, like at the seafloor, and it resulted in a tsunami. So like all the way offshore out in deep ocean, you can have a fault, an earthquake that happens on the seafloor, and that pushes ocean water up and it forms a wave. And that wave, if you're like out in the water, out in the ocean, you're not going to necessarily feel it. But when that wave approaches the coastline, it like piles up to be a huge wave. So in this case, it was like a 10-meter high wave, which is like 30 feet. Tsunami waves can be up to 50 meters high, which is like 150 feet. Okay, so when the wave reaches the shallow water at the coast, the wave slows down, the water piles up, and then you get the large wave that crashes on the coast and floods the coast. But if you were out in the middle of the ocean, you would hardly notice that anything is happening. Prior to hitting the land, the sea withdraws and exposes the seafloor. So if you ever see that happening, like all of a sudden, if it looks like low tide, all of a sudden really fast, that might be a tsunami. But it has to be like low tide happening really quickly in an area that does not normally have that happen. Because there are some areas where low tide happens pretty quickly, but it's not related to a tsunami. There is a Pacific tsunami early warning system, and it uses instruments to detect seismic sea waves and seismographs. So if you're gonna have a tsunami happen along the Pacific, there is a warning system. At the time of the tsunami in 2004 that hit in the Indian Ocean, there was no tsunami detection or warning system at all. Okay, so this is a picture of a tsunami hitting the coast. This is like a small tsunami, this picture. And ground failure is when you have landslides triggered by earthquakes. So like in 1970, there was an earthquake in Peru that triggered an avalanche that killed 66,000 people. Excuse me. A headline, I didn't change that. A headline from September 26, 2019, that's not last week. There was an earthquake and an infant was killed. At least one person was buried in a landslide after earthquake rocks Indonesia's Maluku Islands. So that was about a year ago you had that happen. So I put that link in there. And this is the San Francisco earthquake in 1906 led to fires. So it says San Francisco in flames following the 1906 quake, broken water mains left firefighters without water. The fire was triggered when a gas line ruptured during the Northridge earthquake in Southern California in 1994. So there are two different instances with fires related to earthquakes in California. Then we have this real-time global earthquake map. This is really fun. I'll show you. It's actually really fun. You could show all your friends how much fun this is. So this is an earthquake map, and it shows you the default is all of the earthquakes that are a 2.5 magnitude or more in the past day. So in the United States, in the past day, these are all the earthquakes that have occurred. Just in the past day, like now, basically. And then if you click on the left, this is your magnitude is 2.5, 4.3, etc. And it's sorted newest first, oldest first, largest, smallest. So let's do largest. The largest earthquake that happened today is a 5.2 in Indonesia. No, we didn't feel any of these. I mean, these are like Indonesia, Papua New Guinea, Argentina, Tonga. This is St. Kitts. So like, okay, I'm showing you like how to read it though. So I just made it largest magnitude so we can see what the largest ones. You can also like zoom out and see the whole world. Also, the size of the circle is related to the magnitude. Okay, so here we had one in Argentina. And then when you click on it, it says magnitude, and then it says the depth was 152 kilometers. And then it tells you the time. So right here in Argentina today, you had a magnitude 5.0 earthquake, and the depth was 152 kilometers. And then you had 2 in Chile. This one's a 4.3. This one's a 4.2. Now, by the way, are we surprised that the west coast of South America had earthquakes? Are we surprised about that? Why are we not surprised? Right, the plate boundaries. When we looked at the plate boundary map, you have a subduction zone where the Andes Mountains are formed. So you're going to have earthquakes there. Alaska, you're going to have earthquakes. Like, that's not a surprise. These are very small though. All these are very small. I mean, Puerto Rico, look, you had like how many earthquakes were in the Caribbean today? And Alaska. Actually a bunch, right? Yeah, so you zoom out and you're gonna see that the earthquakes are all happening on the plate boundary, which by the way, they put the plate boundaries on this map. That is really cool and helpful for us. So look in the Caribbean. Look how many earthquakes happened today in the Caribbean. I mean, like, look at Puerto Rico. Look at this. A bunch of earthquakes happened. But we're not surprised because it's on a plate boundary. Okay? I don't know. I think this website's really cool and you could show everyone you know. So look, all the plate boundaries. Indonesia, there's earthquakes. Iran had an earthquake on the plate boundary. Well, just south of it. This was a shallow earthquake. Yes, we will talk about that in 1 second. Okay, so I'm going to shut this. You guys can play with this later. You have the link. Earthquake in Haiti. Oh, I mean, I don't mean to sound excited. I'm just saying like earthquake in Haiti. Okay, January 12th, 2010. This was actually really bad. Really, 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 really destructive earthquake. Really terrible. So the earthquake was very close to Port-au-Prince, which is heavily populated. A very, very populated city. And you can see here, right, Haiti is on the west, Dominican Republic is on the east, and Port-au-Prince is on the map here. The epicenter is just west, a little bit south. And then it shows you the aftershocks. So this was a magnitude 7 earthquake. And here's another picture. And it shows you the earthquake. And then it shows you the population and the damage. And it was really bad. So you see here, like at the top, here's a map of Haiti and the Dominican Republic. Port-au-Prince had, if you look at the colors, you have like extreme and violent, that's your earthquake intensity. Yellow is strong. Wait, let's see. My friend moved from there. Yeah, a lot of people left Haiti and just, didn't go back. That happens a lot of times when you have like a natural disaster. After Hurricane Katrina, a lot of people left New Orleans. They moved to Texas, they moved to Florida, and they never moved back. They didn't rebuild. I think my elementary school had it. Yeah, a lot of people did fundraisers and stuff. And I kind of remember watching American Idol that year, and they did like this whole fundraiser for Haiti. Yeah, but that's good. That's sad that you guys are bringing this up. It's sad like that a lot of people had to move from there. But if you saw on TV or if you know people who told you stories, there was horrible destruction. Just, buildings and just fell, and a lot of people got hurt and died, and just mass destruction. So part of the reason that there was so much destruction is you had a lot of large buildings in Port-au-Prince and in surrounding areas. And they may have been poorly constructed for earthquake resistance. So it's not like in Japan, where in Japan, a lot, like their buildings are built with earthquake resistance. They're designed to withstand earthquake shaking so that they don't break. But Haiti, the construction, there's not like as much, the socioeconomic level is lower. So like they don't have as much money. Wait, I heard this a minute. Yeah, I don't know. I kind of heard stuff. I'm not really sure. There's political and social reasons for what you're saying that I'm not really that familiar with. Yeah. Oh, so yeah, the economics of Haiti, they don't have as much money as, let's say, Japan. So in Japan, where they're building buildings that can withstand earthquakes because they get earthquakes often in Japan, in Haiti, they didn't necessarily have as much money to build earthquake resistant buildings. Also, you have extremely heavy population in Port-au-Prince and the surrounding area. So you're talking about a concentration of a lot of people living among a lot of buildings that are not resistant for earthquakes. So you have this relatively large earthquake, a 7.0 is a big earthquake. So it just led to like complete mass destruction. So like you're seeing your friend moved, a lot of people had to move. A lot of people died. It was just horrible. And then there were also a lot of strong aftershocks, which makes it hard to save survivors among like the rubble of the buildings, because then the rescue workers who are going into the area could get badly hurt while they're trying to like dig out survivors. They may get affected by aftershocks. So there's like all these problems. Now the focus of the earthquake was shallow. So that also added to the areas. When you have a shallow focus, the areas close to the epicenter are going to be like more affected. So the earthquake doesn't really spread necessarily, like the effects of the earthquake don't spread as far if it's a more shallow earthquake. So the Dominican Republic did not really get as affected as much. That's because the earthquake, where the earthquake hit, the way that the waves like traveled to Dominican Republic, it's like it was far from heavily populated areas. Because if you look at like, where is it? If you look at Santo Domingo, it's not that close to Port-au-Prince. So like, that's one of like the main city. Correct me if I'm wrong here, but I think that's like a main city, right? So that's where your concentration of people are. So, but you have all this land in between that's more rural. So like the earthquake affecting rural areas did not really, yeah, right, it's the capital, that's what I thought. So like the earthquake hitting areas in the Dominican Republic that were more like rural areas or like countryside areas, you're not really affecting that much because you don't have like a lot of humongous buildings and a lot of people concentrated. It's more like countryside. So the damage was not as much in the Dominican Republic as it was in Haiti. It just happens to be like where the earthquake hit and the depth of it, and you know, so like all these factors together led to it being like a horrible, horrible thing that happened. Okay, so because there were usually like people want to know like why did Dominican Republic not get affected as much as Haiti? So it's because of where the cities are located, related, you know, relative to where the earthquake happened. That's like the main reason. It's just like the geography of where the cities are. Oh, that's the last slide. So that is it. So anyone have any other comments? I don't know if you guys want to talk about the earthquake or like talk about any other major earthquakes. I mean, there are a few years ago, there was really bad earthquake in Colombia. Every once in a while, there's a really, really major earthquake in Chile. Italy, a few years back, had a really big earthquake. China sometimes, Japan sometimes. The tsunami, yeah, there was that tsunami in Japan. That was an offshore earthquake, right? Yeah. Now, if we go back and look at the earthquakes map here, where is it? This map, I like this map. This is from the Earth Science Reference Table, and this is like one of my favorite plate tectonics maps because it's labeled really nicely and everything. But if we look at, you know how I was showing you the map of like the real-time earthquakes? So when you look at Alaska, there were a lot of earthquakes in Alaska. You have a subduction zone happening there. Okay, look where Puerto Rico is. You have a subduction zone. Subduction is like, it looks like these rectangles kind of jutting out of a black line. So the whole area around here, right? Puerto Rico had like a bunch of earthquakes. right? So this explains also why Haiti had an earthquake, because you have a plate boundary. The Caribbean plate is a different tectonic plate as the North American plate. So there's a plate boundary basically around the entire Caribbean. But that's what formed the Caribbean islands, is its volcanic island arcs. So the reason the islands are there is because of subduction. If you look around the Philippines, it's all subduction. So every once in a while, they get really bad earthquakes there. What else? Okay, so that's about it. If you look at other maps, you'll see like in Europe, you have a country like Turkey is actually like being rotated. So that's why every once in a while you hear like a really, really bad earthquake happen in Turkey. So Turkey is kind of being like rotated a little bit. Okay, so yeah, that's why they get like really bad earthquakes every once in a while. Okay, so yeah, that's about it. So make sure you go through the review sheets. And again, the exam is October 23rd. So make sure like at this point you have metamorphism, plate tectonics, and then today's lecture. Those are 3 review sheets now that you could make sure you finish. Okay, so yeah, have a good weekend. If anyone wants to stay and discuss anything, you could stay and talk. Otherwise, have a good weekend, and I'll talk to you next week. For any of you who might be in a Monday lab, keep in mind Monday, there's no school, and that it's a Wednesday of next week is a Monday schedule. So anyone who has a Monday class, your classes for Mondays are on next Wednesday. Wait, who doesn't have lab? Okay, bye, have a good weekend. Wait, what day do you have lab? Where is my calendar? Oh, right. So there's no, yeah. Yeah, I guess there's no Wednesday, right? There's no Wednesday class because Wednesday is a Monday. Okay. Have a nice weekend, everyone. Right. Yeah, some of the classes are like ahead because of the schedule. Okay, bye, have a good weekend. Thanks for participating.